Hey robot makers, how you doing? Hope you're having a good day so far. So, do you want to know how to use the SSD1306 display with a Raspberry Pi Pico? Then this is the show for you. I've also got some news to share with you. Try that again. I've got some news to share with you at the end as well. So let's dive straight in, shall we? My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. So, the SSD1306. So yeah, the session goals today, we want to get to know what this device is, how to use it with Raspberry Pi Pico, and then do some cool things with it like displaying graphics, text, and maybe a bit of animation as well. And I'll show you how to convert images and convert them so that you can display them on these displays as well. Nice and simple, all free too. So how does this display actually work? So any display is made up of an array of pixels. So the pixels are picture cells. You might not have known that, you might well know that. And the pixels themselves can be colour, grayscale or black and white. And the number of pixels that you have on a display defines the resolution. The more pixels you have, the higher the resolution will be. So these displays are pretty low resolution, it has to be said, and they're very small as well. The pixels are certainly packed into there, but they're either on or off on these, they're black and white. So these actual displays are 128 pixels wide by 64 pixels tall. They are black and white. Now you can get different varieties of these. I've got a mixture. I've got some ones that are white and black. You can get blue and black, yellow and black, red and black. You can get ones that have got a mixture where they've got a top band bit which is sort of yellow coloured and then the bottom bit is blue, and there's different variations of that. So you'll see these when you go to purchase them. And what that essentially is it's still a black and white display, but they put like a colour gel over the top of it, like the old arcade machines back in the day when they were still just like a black and white TV underneath with just coloured tape over the top to make it look more colourful. So they're an I2C display as well, and we'll get on to that. So I2C, it's just 4 pins to get this up and working. And as you can see on here, we have the 4 little pins at the top there. Oops, let's just try and get that into focus. We've got the ground, we've got voltage, we've got clock, and we've got data. And you can see on the graphic on screen there, that's the order. You know, the square one is usually ground. That's how you can usually tell. It's the same on the Raspberry Pi Pico. If you've ever looked at them, they have. If I get one of these out of this new little packet that they come in, I just grab one of these and I show you close up. So on the little castellated edges, on the very edge of the board, you may or may not be able to see, but some of them have got square bits on them. It's not very easy to see actually. But at the third pin down on the right, it's got a square edge to it, and that means that's one of the grounds. So there's several grounds on the Pi, on the Pico. And now the other thing to note on these displays as well is where the sort of coordinate system starts from. So it's the top right, top left, top left. So 0, 0 is top left on these. So that's just bearing in mind when we're sort of positioning things on the display itself. So to get these wired up to the Pico is pretty simple. We just need to connect the data and the clock to the data and the clock on one of the I2C buses. So I usually use the first one, which is just these 2 pins here, pin 0 and pin 1. So we'll have a look at that wired up on the overhead in a minute. So frame buffers. So to understand how displays work and how we can work with them when we're writing programs, we need to understand frame buffers. So a frame buffer is just an area of memory, and it's been optimized to work with displays. So typically you have an active frame and you have a frame buffer somewhere else just off to the side in memory that you can work on, and when you're finished writing and doing all your updates, you can then just make that the live frame. And that stops any kind of flickering or weird glitches, because that display may have to be refreshed, and if you do something midway through a refresh, you'll get kind of an artifact displaying there. So we tend to work on frame buffers in a different area of memory and then just switch them in. We have some kind of show or display command. So every frame buffer has 3 different dimensions to it. It has a width, it has a height, and this doesn't need to be the same as the actual display. You could have this larger or even smaller. So if you was working on like an icon, you could have a much smaller frame buffer just for that particular icon. and then you can write that to anywhere on the display. But we're going to create a buffer that's the exact same dimensions as the display. So it's 128 pixels by 64 high, and the bit depth is what we talked about before about the color. So because this is just a monochrome display, just black and white, it has 1 bit to display each pixel. So let's have a look at bit depth a bit further, a bit more in depth. So it essentially defines the number of colors that are available to us. So if it's black and white, it's said to have a bit depth of 1. So the pixel is either on or off. Now you can then, the next one up is 4 bits. So you can have shades of grey. You can have 16 shades of grey, not 50. The next level up from that is 8-bit colour. And what they've done there is they've taken a byte, which is 8 bits, and they've said the first 3 bits of that are going to be representing the red. So there's 3 bits for red, 3 bits for green, and then only 2 for the blue. And that's because our eyes see a lot of blue in nature and we don't need as much definition on that. So the choice was taken to do that. Now there are some colour systems where instead of doing that kind of mapping there, they have a colour table and the 8-bit value just references a particular value in that table, and that's what's then displayed on the display. And if you're as old as I am, when there was a display, was it called MGA? And that one had colour tables, 256 colours, but you could actually change the colours and you could cycle the colours and do some crazy things without actually changing the buffer on screen. The next one up from that is 16-bit colour, so we're getting into some really good colour depths now. So we've got 65,000 colours that we can display. Again, like the 8-bit one, it's sliced up into 5 bits to red, 6 bits for green, and then 5 for blue. And again, that's because our eyes can actually differentiate lots of greens because of nature and we see around us. And then finally, true colour. So 16-bit was called high colour actually, 8-bit is VGA, and 24-bit is true colour. So that has 16 million colours, and we have a full byte for each of the red, green and blue. So we've got the full definition there. Now the thing with bit depth is that's great if you want to have a very, very high resolution screen with a really good graphic, but the memory usage will be affected. So typically on our Raspberry Pis, these have, you know, quite low memory. The actual SRAM is quite small on this. It says on screen there 264 kilobytes of storage that we can use, and some of that's being taken up by Python running itself. So we need to think about that when we work with displays. We can't have a massive 4K display running on a Raspberry Pi Pico. It just wouldn't work. There isn't enough bits in its memory. So if we've got 128 by 64 times by the 1 bit for our bit depth, that means we need 8,192 bits to store that in memory, which is 1 kilobyte of memory. That's not a lot at all. If you think we've got the 264 to work with, it's not even a percentage, is it? So not even 0.5%, it's just slightly less than that. If we actually had a display that was 128 by 64 times 8 bits, so it had the 256 colours, that would take up 8 times the amount. So because we're using 8 bits instead of 1, so that would be 8 kilobytes. So that would be more than a percentage of the memory available, just about. If we then had 16 bits, you can see there it was 16 kilobytes, and again if it was 24 bits, we would need 24 kilobytes of memory just to store that very small area of memory. And we might want to have many buffers as well, so if we're working with animation, each frame would need that exact amount of memory. So you can see there the difference between having true colour, 24 bits, versus a 1-bit monochrome display, which uses hardly any memory at all. So that's really going to work well for us in our projects with robotics, because we want to keep as much memory as we can available to us. So that's memory usage and what we need to think about there. So if you like these videos, I always welcome you to like, comment and subscribe. You can like this video if you're watching on YouTube. If you're watching on Facebook, you can also give it a like on there as well. That does actually help the YouTube algorithm, which is the main place where these videos get stored and discovered by people. But I am broadcasting this using Restream, so you'll see it on Facebook, inside the SMARS community, inside the Small Robots community, on my personal page, and also on YouTube and Twitch as well. I think it did used to go out to Twitter and Periscope, but I believe that's been cancelled now. So yeah, it can help me out if you leave any of those things, or if you want to watch a different video at the end of this from my library of videos that's growing every day. That also helps out. So frame buffers. So we talked about frame buffers just a moment ago. And Python has a really useful library for us that's just called frame buffer. And it's even included in the MicroPython, which is fantastic for us. And there's just a couple of commands there that we've actually got available to us. So filling an area. So if we want to just fill the entire frame buffer with zeros, just blank it out, we can say fill brackets 0. If we want to set an individual pixel, we can do that using the pixel command. We just give it an X and a Y, and again, the value, the color that we want to put in there, which is going to be either 1 or 0 for us. And then because this is because we're working with rectangular displays, there are optimized commands for drawing lines. So you can either have a horizontal line, a vertical line, or a diagonal line. A diagonal line will take a little bit more work for the computer, because horizontal and vertical lines, you can do some tricks behind the scenes to set them, because they're going to be in consecutive memory areas. Then we have the rectangle command, so that's essentially just drawing 2 horizontal and 2 vertical lines connected at some coordinates. So that's useful for putting things in. Bit of vogue going on there. We can fill a rectangle, so we could have that filled with whatever colour we want. On our black and white displays, we might set something to be like a white background with some black text on it, for example. We can draw text. This is really cool. So we don't even have to bring fonts or anything. We can just go straight to the text command and write some text to our display. So we'll have a play with that in a minute. It works so simply. And then we can scroll. We can actually move the text in a direction of our choice as well. And again, what it's really doing is just picking that up and moving it across in memory. So it's kind of doing a memory map function on that. Then we can do something called blit, which is a way of writing to the display very, very quickly. So bit blasting, or blit, which is what it is, the command here, writes the consecutive number of bytes to memory very, very rapidly. So that means instead of having to turn on pixels one at a time, we can basically just set something in a buffer and then just blast that buffer into memory. And it just does a mem copy straight into the live display. So that's frame buffers. We'll be using that for sure. And then how does a display cycle work? So I talked about this a couple of minutes ago. So when we make a change to a frame buffer, we're actually making changes to an area of memory, and that isn't displayed until we tell it to be displayed on the live display. So these little displays have an area of memory on the chip, and we need to move whichever buffer we've got into this little chip by just squirting those bits down the I2C bus. And that only happens when we tell it to. So sometimes if you're working on these programs and you think, why is nothing changing? You might not have done the show command, the display command, to move it from the frame buffer into your live display. And that prevents the flickering that we talked about. On some of the very early computers, they didn't have this frame buffering. They just had one area of memory, and you wrote directly to that, and whatever was in that memory got displayed on the screen. And one of the issues with that is if you caught that midway through it doing its scan cycle, you get kind of half a graphic, or you get a graphic that seems to flicker in a weird kind of pattern. Some people use that in arcade machines to make the sprite, the little character, flicker on the screen. So they intentionally did that, but they understood, the scan sequence and how to wait for that. But we're not going to do that. We're going to actually have a special area of memory, a frame buffer. We're going to then write that to our live display. So we just need to bear that in mind. And then animating the display. So this is where it gets really cool. Now, if you remember back, let's see if I've got one of these to hand. Get one of my many SMARS robots. We've actually built an animated display for our SMARS robot before now. We've got this 8x8 display, so it's 64 pixels there. Not massive resolution, but we made this animated. And what we did is we just drew a face, a smile, we had a blink, we had a sequence of these, and we could make it sort of do all these different animations. In fact, if I just put some power to that, you might just be able to see there. It looks like it's flickering, but that's just the camera refresh rate as well as this display refreshing. But yeah, you can see there, it's got his little face. And if I hook that up using the Bluetooth there to my phone, I could get it to change which face it's got. And we can animate them by just having a sequence of frames with a small delay in between each of them. So we can do that with bitmaps, with our frame buffers. We just need to have a frame buffer for each of the frames, and then we just need to swap them out using some kind of loop. So we will build that, and we'll get a little animation going on the display. So I have one just ready to go over here. In fact, I'll just plug that in so that we're ready to go. And let's see if that comes on. I'm just going to get my Visual Studio ready, and I'm just going to click on run there to see. Yep, it's running the little test program, and you can see there what's going on is we have, I just do that, you can see the little face there. I've got some eyes that are sort of just going to the side like that. So that's just 3 frames, and we'll look how to build that in a demo in a second. So can't wait to show you this. Okay, so that's all that an animation is. It's just a sequence of frames with a delay in between each of them. So if you want to go and grab the code, I had to find a version of code that would work with the latest release, the official release of MicroPython. There are some libraries hanging around from Adafruit that don't work anymore. So the version I put on the link there does work with Raspberry Pi Pico and all these displays, which I've got a myriad of these. So as long as it's a SSD1306, it'll work fine. So created by Adafruit. Thank you, Adafruit, for creating that nice piece of code. And I've just made that work for us. Okay. So one of the things we want to be able to do is we want to be able to work on a graphic ourselves and then convert that to whatever format works best to display on this little display. So there's a couple of tools that we need to use for this. We need something to create the original graphic. Then we need a conversion tool, and then we need to upload that converted file into our Raspberry Pi Pico and have a routine that can read from it. And these things are actually quite trivial to do, to be honest. I was able to do this at lunchtime today, so if I can do it, so can you. So the tools I'm currently using, if I just go to this one here, I've got Adobe Illustrator. I'll just shrink my screen down there so you can see what's going on. And I've just created a small graphic, as you can see there. Now this is actually a full 1080p graphic and these are vector, so there's no actual pixels on this. This is just, you know, a very smooth vector. And what I've done there is I've just grouped these eyeballs together there so that we can do things like that. So if I put these eyes to the sort of top there, I can just save that out as a PNG file. For now, that'll do. So if I go to save, I'm going to save this as frame 4. And it's going to be a PNG file. So I'm just going to say OK. The screen resolution's fine for that. And then what I'm going to do, I'm going to load up GIMP, which is the graphical... what does GIMP stand for? Let's have a look. Graphic Image Manipulation Program. Very exciting. So I'm going to open up that PNG that I've just created, which is frame4.png. So if I open this up here, you can see we've got this great big graphic. And what I want to do is I want to convert this from being a full colour into being black and white. So the way that we do this, we go to Image. Let me see if I can get that so that you can see the screen a bit better. There we go. So if I go to Image, I then go to Mode, and at the moment this is RGB. I'm going to drop it down to grayscale first of all. Now we don't see any difference because we didn't have any colours on there to begin with. And then I'm actually going to move it to Indexed. And there's an option on this Indexed here to use black and white 1-bit palette. So that's what I'm going to select there. So I'm just going to do Convert. And then what I'm going to do is I'm going to scale the image down. So there's an option there to scale image, and then it asks me what's the width. So it's 128 by 64. I'm just going to say scale. Now it will get a bit sort of crunchy, the graphic, a bit pixelated, but that's the small display for us. There's nothing really we can do about that. Then what I'm going to do is I'm going to go to File, and I'm going to go to Export As, and then down here we have Select File Type, and I'm going to go and find the portable bitmap file. So it's called PBM file. So I click on PBM, I click Export, and it will say, do you want RAW or ASCII? And I want RAW. So I'm going to say Export RAW. And what I've now got is a file. If I just go back to my Visual Studio, if I just zoom in a bit here so you can see. So we've now got frame 4 PBM, and it says there, let me just go back to open it in the correct area, frame 4, and let me just do that so you can see. It's just saying, do you want to open it anyway? This file isn't supported. And you can see there we've got 4 lines of text. 3 of them we can read, and the 4th one is just lots of question marks. That's actually just data in a very specific format. But we can see there, it's converted our program to something that we can read with Python. So let me get back to the keynote and we'll look at this a bit further. So this image conversion, I'm going to use GIMP to convert the file, any file, to the PBM format. Portable bitmap, which is a black and white text-based file format. Now GIMP is free, completely free open source, so you can go and grab that. That works on Linux, Macs and Windows. Not sure if there's a Raspberry Pi version of that. Anyway, you can download that for free and you can just do the steps that I've done there. So we open our file, we change the mode from RGB to indexed, we select 1-bit depth monochrome, and then when we go to export it, we choose PBM format and we make sure that it's raw, not ASCII as well. So let me go to the next slide. I'm just going to have a look at some of the comments because I can see some people are making some comments there, and I also want to make sure I'm not missing out on anything there. So good stuff. So, and Samo was just saying he's watching from Germany, from Nuremberg. We've got Adam as well on the stream, and Tom. Hey Tom, I promise not to show any of your personal details this week. And Adam says you can use GIMP instead of Illustrator. Yes, you can. You can use Inkscape as well, which is a free open source alternative version to Illustrator. I wanted to up my skills with graphics. I do a lot of graphic design stuff as well, as you can probably tell from the look and feel of this show. And I wanted to sort of move from OmniGraffle, which is a Mac-only piece of software, to using Illustrator, because it's got a lot more stuff you can do there. And those skills are transferable between Inkscape and Illustrator, but I already pay for Adobe Creative Cloud, so why not? Yeah, Adam is saying you don't need to go to grayscale if you're using 1-bit index. You could just jump to that. I was just following a tutorial I read earlier just to make sure I did it correctly. And you didn't know that MP supported PBM. MP MicroPython. Yes, it does, and we'll see how it supports that. And Mac and RPI. I did not know that. Awesome. Right. So let's get back to the keynote, and we can then let's see what else we need to do. So the contents of this PBM file, let's have a read through this. So what are these different things? The first number is the magic number. So you can see there it can either be P1 to P6, and depending on which format we've chosen in when we've been exporting the file from GIMP, defines which of these magic numbers. So there was another format that we could have chosen, which was the portable grayscale bitmap, PGM, or we can choose PBM, which is the bitmap one. So I've gone for the bitmap, so I'm going to be either a P1 or a P4. I didn't choose ASCII, I chose raw, which is binary, and that's why P4 shows up there. Then we get a user comment, which is just the graphic creation program that created this file. So it says there, created by GIMP. And then it has the image width and the image height. And then line 4 is all the data. So that's all the the ones and zeros that make up our graphic that we just created, which is those eyes looking up. So that's what we need to know. Just we could just read in 3 lines and throw them away. And essentially that's what we will do. We just want to get to that raw data and put that into a frame buffer. So I also want to just make sure you're aware that I do create a new video every Sunday. Typically it's around 6 or 7 o'clock Greenwich Mean Time. It's always 7 o'clock my local time. But if it were in British summertime, then that might be 6 o'clock GMT because we're in BST right now. And as I always say, if you're in the Americas or Canada, you'll probably be in the left-hand column. If you're in the European zone, India, Pakistan, Russia, you'll be in the middle column there. And also if you're in China, Australia and Russia, you're also in the right-hand column. If you've not checked out the website, smarsfan.com, have a look over there. Last week I launched a new Smars learning platform. So on there was Robotics 101, which is a real introduction to robotics for people who've perhaps not touched the robotic arena before and they want to sort of get started on that quickly. There's a Python 101, which is an introductory course into Python, and there is how to build a SMARS and a SMARS quad robot as well, so you can build one of these little robots for yourself. So that's all on smarsfan.com. And also, if you want to help out the channel as well, you can head over to buymeacoffee.com, and that can help pay for all the equipment, software, hosting, and so on, and all that funky music that we had at the very beginning of the show as well, which I have to then edit out, so you don't get to benefit that if you're watching this on playback, but there's at least a 5-minute intro. So yeah, if you want to help out the show and help out me, that's how you can do that. So let's get back to our keynote. Demo time, my favorite time. Right, so let me just bring up Visual Studio. So I'm just going to plop over here in the corner, and what I'm going to do is I'm just going to bring this divider line down here. So what I've got going on, I've got this one that says Pico Cat on it is a Raspberry Pi Pico that's just wired into my Mac, and I have a little display which has just been plugged into the I2C bus, and I'm just using the pin 0 and pin 1 just on the Raspberry Pi there, you can just see. I've chosen to use some header pins that can receive jumper wires or DuPont cables rather than having it in a breadboard, but I could use the one that's on the breadboard there. I think that might be one of the ones I've blown, I'm not sure. But I've got plenty of pies. We can always, there's always more pies. So that's wired up there. I've got it to my display, and this machine that I'm connected to is running Visual Studio, and I've just got some code that I've created. So let's have a look what we've got going on here. So if I just go to, first of all, this SSD1306.py. So this is the library that Adafruit wrote that enables us to do everything that we need to do. So there's a couple of constants there, and what they essentially are is all the different commands that the display will receive. They have a very specific hexadecimal value, and we just want to know what that's called. And even then, they don't look very friendly. We don't need to worry about that. We have some nice friendly commands. So there's a class that's called SSD1306. It's inheriting the frame buffer object, which is that library that we talked about earlier, and it just initializes that. It even calls the initialization thing of that frame buffer. Then we have an initialization of the display, so it just wipes all the memory values to 0, sets it up and so on. And then we've got some power on, power off, contrast. I don't think we can do contrast on these displays. I think they're either on or off, but this library is written for, maybe we can. I've not played with that. We have invert, which will flip the pixel value from, if it's black, it'll flip it to white. And if it's the whole display, it'll reverse the entire display, which is quite useful. You can use that to just make it flash as well, which is quite cool. And then the show command, this is the most important one. So once we've done some stuff in the frame buffer, we want to show that on the actual display, on the OLED display, then this is the command that we use. So we don't need to worry about how that works, we just need to know that it does work. Then there's a version of that library which is specific to the I2C bus, and then there's a version which is specific to SPI. So some of these displays, I've got a slightly different display here. This is 128 by 160, and this one is an SPI display. And you can see there it's got a few more pins on it. If I sort of hold that there, you can see it's got 6 pins rather than the usual 4 that we have for I2C, and that's even got a memory card holder in it. So I think that's a colour display as well, but we're not looking at those today. So that is, for all intents and purposes, that's what we're going to be using. We're going to be using that class there, which inherits all the things from above and just has some specific things for I2C. So let's get over to our demo program. So what I will do, I'm going to create a new file actually, just so that we can do this from scratch. So let's call this test.py. I might just have to refer back to the other one. So the first thing we need to do is import machine. Import from machine. Let's try that again. From machine import, and we need the I2C. We need pin think that's everything we need. We need to import sleep because we usually use sleep commands. We certainly need to import from the SSD1306, import the SSD I2C version. And do we need anything else? Let's also import the frame buff as well. Okay, and Visual Studio doesn't recognize either the sleep or the machine or the frame buffer, but it's fine, it will work. So the first thing we need to do is just set up our I2C bus. So you've probably done this a couple of times if you've been following these videos. So Raspberry Pis have several different buses on them for I2C. There's a poster that you can download from the Buy Me a Coffee store if you want to have your own version of... oops, that's not the right image. Oh, I'll pull that camera out. Anyway, on my wall that we saw earlier, I have an array of posters, and one of them is the Raspberry Pi Pico. So if you want to know what the pinouts are, you can just refer to that. So the SDA is going to be pin 1, and the SCL is going to be pin... No, that's the wrong way around, isn't it? Pin 0, and then that's going to be pin 1. Okay, and then our I2C is going to be the I2C class, and then we just say ID equals ID, SCL equals SCL, and SDA equals SDA. And that's just going to set up the right pins. So that as long as we're using the right pins in the right sequence, that will work fine. What I usually do as well, I will do an I2C.scan. Let's actually just put that in a print command, just so that I can see has it detected it. So I'm just going to do run. I'm just going to stop that from running, and I'm just going to say run. So it can't find sleep, and that's because sleep is actually in the time. So if I say from time import sleep, that will actually work. Let's try that again. Expecting a pin, of course. So these need to be wrapped in the pin, which we did bring in the import. Oops. And that's just defining that that's actually a pin of the Pico. Right. Is that going to work? Okay, so there we go. So it's detected a device, and the value of that is 60. So that's the default value for all of these displays. If we want to actually change the address of this on the back of the display, if I can get that to focus there, there are a number of... if I just get a pencil or something, I might be able to show you this a bit better. Right, so on this display, there is a number of address select things just here, and you just need to solder them depending on which address that you want to change that to. So if you've got two displays, if you've got two eyes, for example, you'll need to just apply a bit of solder onto that. But the default value is always 60. In fact, the library defaults to that value. So if I have a quick look into that SSD1306 library, and I just scroll to the top there, see where it says 0x3c. If I load up the calculator and I just type in, was it 60 in decimal, and then I go to base 16, that's 3c. So that's saying there that it's going to default the value to that. So we don't even have to tell it what address this is on. It already knows, it already guesses that. Right, so that's that means we've detected it, our wiring's correct. So what we're going to do next then, let me just have a quick peep over at our display. So we're going to set up this OLE display. So let's just borrow that text there, and I'll just explain what this means. Sorry about that, just went to the wrong button then. Right, so what I want to do is I want to go to back to our test program and just paste this in. Yes, oops, I should have done the be right back technical issues thing. There we go. It just ran the wrong scene. I've got scenes set up on my screen, and I can just I don't know if I've ever shown you my my toy for changing all the different scenes. It's called a Stream Deck. and you can just sort of change all the different scenes with this thing. And they're essentially just a shortcut or hotkey. And instead of pressing paste, I must have pressed a key that made it change the scene. So that's all that's going on there. Ignore that. Right, so I'm calling this display OLED because that's what it is. I'm bringing in the class there, which is the one from the library, which is the I2C one. The width of it is 128 pixels, the height is 64, and we're passing in that I2C bus that we've just defined there. So that's our display nice and set up. We do need to initialize our display, so we can do OLED dot init display, just like so. Doesn't need any parameters. And let's type a little hello program. So let's do text. And let's make it say hello world. I'm going to have that at, I think it's x equals 0 and y equals 0. Can't remember if you need those in there or not. So I'm just going to run this, and I'm going to show you on the overhead what happens when we do this. So if I go to here and I click run, nothing happens. So I think what the problem is there is it just doesn't need the x and the y, it just needs the values. Right, so we can't see anything on that display at the moment. There is no text appearing, and that's because if you remember before when I talked about, we just made the changes to the frame buffer, but we haven't displayed it. We haven't set it to the live display. So what we need to do is just do the show command. So just by adding that, it will actually make the text display. I don't know if you can see there, but that actually says hello world. If I just hold that display a bit higher to the camera, you can just about make that out. Because it's a display, it's a bit blurred but you can make out that it says hello world. There we go. So that's great, that's working. The other thing we can try is just inverting the display. So after that show command there, let's do OLED dot invert, like so. And I'm just going to do run again. Oops, what's it complaining about there? Oh, we have to say what do we want to invert? Do we want it to be black or white? So I'm going to say one, which is white. So if I do that, run that again, let's see if that's going to run. Yep, you can see the display has now gone to white. However, the text that was previously white is now black. You might not be able to see that there, but the hello world is actually now black on a white background. So it has inverted the entire display. So that could be quite useful to use if you want to sort of flash the screen and bring things to people's attention. So that's how we do text. We can do rectangles, we can do lines and all that kind of stuff. But the thing that I find most fun is graphics. So that graphic that we just created, which was those eyeballs. So if I just go to that display there, that's the PNG. We then converted it to this PBM format, which is that. I do need to upload that to the Pico, so I'm just going to click on the upload button. That's going to load it to the flash area on the Pico, and now we can actually work with that within our program. So let's do this. So what we need to do is we need to create a frame buffer. So I'm going to call this FB, and this is going to be type framebuffer.framebuffer, like so. And then we need to say what the dimensions of this are. Let me just double check on my test program. So we need to say what the data is and what the X and the Y, and then more importantly what type of frame buffer it is, because this frame buffer is a library that can do all kinds of frame buffers. So I'm just going to grab that piece of code there, bring it across into our test program, and I'm going to show you what that does. So just before we get into that, so with open is a file command, and we're going to bring in a file. So instead of it being test image, we're going to bring in frame4, like so. So that's the converted file. RB just means it's like a read-only and it's a binary file. As f, which is just a variable, so we can just, in this little loop here, we can say f.readline. So those first 3 lines, we're essentially going to read them and throw them away. So the magic number, we don't care about that. We know because we created this that it's going to be a raw format and it's going to be monochrome, so P4. We don't really care about who wrote the program, that it's GIMP. And we don't really care about the dimensions because we know that it's 128 by 64. The bit that we are interested in is the data. So we're going to load in all the weird question mark things which actually contain zeros and ones into this data, and we're going to read it in as a byte array, which is just, as you'd imagine, an array of bytes. So if we do that, we could actually print out that. So if I just save this command, what I'm going to do is I'm going to upload this test program. And if I just go in this REPL down here and I do import, well actually from test import star, it will actually run that program. And it's complaining because of that line 26 there. Let's just comment that out, upload it again and then run it again, sorry. So yes, if we just do from test import star, it will run the entire thing. So you can see there we've got the, well, you can see there if we've got the white text, the black text on the white background, and it's finished running, but all them variables that we just created and all those values have actually been loaded in here. So if I now go, if I just say data, we can have a look what's in there, and we can see there's lots of Fs, which are values in memory, which are either going to be zeros or they're going to be ones. And because each 0 and 1 is within a byte, those bytes are being interpreted as being characters, because 8 bits makes up a byte. And if we're just sort of saying ones and zeros, and we don't really care about we care about them being a frame rather than them being characters, and this is just how it's represented. But that's what it looks like as a byte array, and the B there means there's a big string and we can interpret that. So that's what we're going to load into our frame buffer. We're going to load in data. We're going to say that it's 128 by 64, and then what we need to do is we need to say frame.buff dot. Now what this next thing is, it looks a bit of a weird command, but it's to do with the frame buffer library can work with any orientation of display. So remember when I said that the orientation is top right is our 0, 0. It might be that on some other displays it's bottom left is 0, 0, or it works instead of left to right or top to bottom, it's got different orientations. So essentially what we need to do here is just tell it that this is going to be now have I got that correct? Is it HLSB? Let me just try that and see if that works. If that doesn't work, it means I've got it the wrong way round. Let me just go there and see what it says. Yep, so it's not that, it must be HSLB. I'm sure you enjoy my live coding, don't you? What I'm going to do is I'm just going to check my display. If I got them the wrong way round, there we go. Let's just grab that. Okay. So what's happening there is we've created another frame buffer object that's called FB. And that's what we're going to use to write to the display. We're going to do that blit command where we just copy it directly onto our display. So let's try that. Let's say OLED.blit, and then we're going to pass in our frame buffer. I'm going to say write this, overwrite completely the frame buffer, the live one, and when I say completely overwrite it, we're oriented at the 0, 0. We could offset it if we wanted to and have the entire graphic move around, but we want it to be like so. Let me just run that and see what happens. So if all goes well, we should see the graphic of the eyes looking up, and I don't think that has worked. So what's gone on there? So yes, so I've not done the display. We need to do show. That's the bit I'm missing. Let me try that again, and we should see when it runs that. There we go, the eyes are looking up. It worked. Fantastic. So if we want to animate this, it's just a matter of reading in those files and then having some kind of pause. So if I go back to our display program for real, all I've done there is I've created, let me just go over to here so you can see this. All I've done is I've created an images array, and then I've said for n in range 1 to 4, because I've got 3 frames. I'm not going to include that one with the eyes looking up. Maybe I could do. Yeah. In fact, let's do that. I'm going to make that 5. We always do like n plus 1 when we do these loops. And then we say with open frame, and then there's this little percentage s in the middle. And what that's saying is all these are frame 0 something, because we're not in double digits, and the ending .pbm. And then what that there means is that that is essentially our loop. So when this goes round the first time, it's going to be 1, so it'll say frame 1.pbm. When it goes the next time round, it'll be frame 2, and so on. Again, we're opening up as a read-only binary as f. We're throwing away those first 3 lines. We're reading in the data as we did before, and then we're adding this, to a frame buffer, but then appending that to our images array. So at the very end of this loop, we will have an images array that's got those 4 images in it. And what I did is I then created a while loop that says for I in images, so loop, iterate through all of the items in the array, invert the display just to make sure that it's always the correct, we could actually take that out to be fair, but just make sure that it's black and white, black with white pixels, blitz the value of I, so whatever is in the frame buffer I, at the coordinate 0, 0, show it, and then wait for 0.1 of a second. And then what I did, I didn't even know you could do this with these loops. You can use reverse. So I was figuring out how do you do the opposite. So it's like an animated GIF that can loop. So the eyes look that way and then the eyes look back. So it means I don't have to create another 3 frames. I can just reverse the order of them frames to make it kind of reverse back. So if I just run this, I'm going to go back over to here so you can see this as I click run. I can see the test program, and then look, it's going up and then it's going back. So it's doing this animation. So how cool is that? That's how we can make an animated display with an SSD1306 and a Raspberry Pi Pico. So what I'm thinking with this is we can get something like this and update this display to be a lot more high resolution. We can show a lot more character in our display, and it can look a bit more like the Vector robot. So it can sort of frown, it can be surprised, it can cry, it can do all those kinds of things with a lot more depth and character than just 16 by 16 pixels. So I just need to 3D print a holder for that. I'm thinking about putting a servo on there so we can actually move the head up and down, maybe left and right if we had 2 servos. But we certainly could do that, and we can add that to our Pico Smarts because this is all Pico powered, of course. And what I've got on here next to the on-screen camera is just some more tiny 2040s. I don't know if I can get that to focus in. I might be a bit too close there. So these are Pimeroni 2040s. So they're very small. There's one with some header pins on. And these are what I'm using for the Smars Mini. So I've got a couple of them, and I've also just ordered in some LiPo micro boards as well, which means we can, I think that's one there, we can power this with a LiPo battery. So I've got some LiPo batteries on order too, so I can start adding these to the project too. So they've got some nice GST connectors and a micro USB on the other side there, and that can help charge the battery when we're not using it, rather than having to swap out a 9-volt battery. So that's that. Let me get back over to our keynote because I have got another thing to update you on, and it's to do with community update. So I had too much time on my hands to create this graphic, clearly. There's like a giant baby. I don't know why that graphic is so large compared to these other people. It's not proportionate at all. So there we go. Anyway, Small Robots group, Man Alive has had a bit of a growth spurt. So if you are a member of Facebook and you're not a member of Small Robots, you certainly need to make yourself a member of that. It's a group that I run, I host it, I moderate it, and it's gone from 500 members back in February this year, 2021, to over 5.3 thousand members just today. I think we might even be at 5.4 now. So if you're not a member of this community, certainly make yourself a member, and we can talk robots. We can share what we're working on, and it doesn't have to be SMARS related. It can be small robots, any kind of small robots. So I'm still working in the SMARS community as well, but this is for other robots as well, such as the Auto DIY, for example, or the OpenCat, Pico Cat. So I just wanted to share that extra piece with you as well. And I think that is all my stuff for today. So hope you enjoyed this. I'm just going to have a quick look through the comments and see what people have been talking about. So, oh yes, we've had quite a few comments going on here. So Tom was saying, maybe use function instead of bitmaps, e.g. circles. Yes, there is a circle command in there, I believe. I remember learning about how to do a circle, using cos and sin back in the day when I did computer science. And one of the challenges there is missing pixels, because depending what size the circle is on your screen, how do you make it so that it looks like there is a consecutive circle rather than missing pixels? So it's quite a complicated algorithm to draw a circle. Adam was saying, trust me, just been testing the mode conversions for e-ink displays on ESP32s. I can only imagine. So you're saying, don't save program comments and just make sure use all the 7.3 naming conventions. Yep, and Tom was saying with his SMARS, he built the eyes using rounded rectangles. And they load faster than bitmaps and are more flexible. Yes, absolutely. Changing the variable, you can then make the motion instead of creating several bitmaps. Absolutely. So yeah, it's definitely quicker to work on the frame buffer than sort of loading in, having, because I was thinking that the more frames you've got, the more memory you're taking up. That's not great usage. Probably be better to read them in as you go and then throw them away once you've worked with them, rather than using all that memory up. And Noah says he's been working on designing his own knockoff SMARS, but for some reason Dabble isn't working. Any suggestions what to do? I've not used Dabble on MicroPython yet. That is on my list of things to look at. I'm just going to load up Dabble on here. So Dabble is an app that you can get for your mobile phone, and there's a really nice gamepad option on that, and you just need to connect. And for example, this robot that's got an Arduino on it has the Dabble library on there, so it's waiting to receive commands, and I've set that particular one up so when it receives like an up command, it knows how to roll the robot forward. So I'm not sure what's going on there. I do know that Dabble works with MicroPython. I'll have a look at that. So yeah, Adam was saying, what is Dabble? It's a really cool library. So not only can you do the gamepad, let me just load that back up. So not only can you have like a gamepad like this, there are different options for it. If I go back, there is, where is it? Or maybe it is on there, but it's the different mode. Yeah, there's a digital mode, a joystick mode. If you go for joystick, then you've got kind of a wheel you can move around there. Or if you go to accelerometer mode, when you tilt, you can see there, as you tilt this, that control will move, so you can actually use your phone to make the robot move. It's very, very cool as a library. I did do a video on that, which was the Bluetooth video. So if you go and look at the Arduino SMARS Bluetooth video, you'll see me set up and use Dabble. So yeah, Noah's just saying there that it's an app you can connect to Bluetooth model, and anyone can help. I believe I'm just using the HCM10. So one of the weird quirks with Bluetooth is if you're using an iPhone only works with Bluetooth modules, which are, I'm going to say, version 6 to 10. Anything that's lower than that means it's not low power Bluetooth. It's not Bluetooth 4.1 or up. And it's because Apple didn't want you to waste all your battery power on not low power Bluetooth, because it is a real power beast. So I was saying oops when I didn't get that working in II because of our little animation, which is still animating as we speak. It'll carry on doing that forever. There we go. That must mean my pizza's ready, so I'm going to have to drop off now, but hope you enjoyed that show. And I really enjoyed doing this one, putting together the displays, and now we can build a more high-resolution face for our SMARS robots, and maybe for other robots too, like the InMove, make some eyes. Hope you enjoyed this. Let me know what you think in the comments, and I shall see you on Sunday for the next video. Bye for now.